All right, I'm Harlan.
I'm Jonah.
And then in the back, we got Yuki, Deep, Derek, Kabila, and Fong. And then also our graduate assistant, Yuhek. So we're going to be talking about machine learning and AC power flow. Do you want to go forward? All right, so basically, power generation and distribution relies on a huge interconnected grid that often spans whole states, countries, or continents. We have about 9 grids that cover the whole North America, all of North America. Now, within each of these grids, there's a few substations that have to decide which power stations generate how much power and how to meet the demand of the whole system. You want to make sure that you have enough power that all the demands are met, so you're not having power shortages, but also not producing so much that you're wasting energy. And the way we simplify this is you can break the power grid up into 3 main components: buses, which is just anything that has a power demand, so like your houses, your factories, but also your wires, because they have resistance, which expends power as electricity goes through them. You have your generators, which is anything adding power to the system, like your solar farms and your power plants. And then you have branches, which is just any place where these generators and buses link together. And we model these as a network where buses and generators are nodes and branches are edges. And solving this system for the optimal generator settings that meet power demands and minimize operation costs form the basis of OPF, or optimal power flow. So it's a complicated problem, won't go through all the equations, but the important thing to note here is that there's a very strict adherence to physical laws. There are basic laws of electricity that have to be met, and if the generator settings don't meet them, then the generator settings are invalid. The important ones to note are power and voltage. Because it's AC, it's modeled with imaginary numbers in addition to real numbers. So you have an imaginary component of the power, which is the reactive power, the real component, which is the real power, and then for voltage, you have voltage magnitude and voltage angle. And all of these have to be set within constraints that are limited for each generator or each bus. If you can't go over them and you can't go under them, or else it breaks the system. So when solving OPF, the traditional way to do it is with numerical methods. The issue is you're often working in a very, very high dimensional space, often hundreds of thousands or millions of parameters if you're modeling a real power grid. And the problem is non-convex, which means you can get a numerical optimizer that gives you the correct best answer if you get a close guess, but often numerical methods will get you to a local minimum, but not to the global one that you really want to find. So good optimizers do exist that each power grid has kind of industry standards, but they can take up to 15 minutes to solve, which is an issue because operators within these power stations like this one here, of which there are 100 across North America, have to constantly be setting generator settings throughout the whole grid. So they have to project what they think the power demands are within a feasible range based on the outputs they're getting from these optimizers. But if you can only get results every 15 minutes, then you're setting generator settings to whatever they were 15 minutes ago. So you have to increase generator settings to meet whatever the feasible changes would be within that time frame. But if we can find a method that significantly reduces those computation times, operators can set generator settings more closely to real demand, which can reduce the amount of fuel used up, which saves money and reduces emissions. So that is our end goal of the project. So the way we think we're going to do this is with machine learning. Machine learning has a few benefits over numerical methods for solving OPF. First, you can decrease computation times. Second, you could bypass the non-convexity of the solution space. It's something that's not as big of an issue for machine learning as it is for numerical methods. And you can build an estimator that then gives a guess that you can put into your higher fidelity model so that you can still have the same accuracy, but you get there much faster. But things we have to look out for is machine learning can give you results that violate those physical laws that we were talking about, therefore giving you generator settings that could never work. And it's very limited to specific network topology. If you have a system with 30 buses and 6 generators, the learning that you do on that system is not scalable to the learning you would do even just on a 31 bus system, because it's a completely different network. And to do this, we use MapPower, which is a plugin for MATLAB, which is kind of the research standard for simulating OPF. It has hundreds of predefined systems that you can bring up and solve and modify, has multiple numerical methods you can choose from, and we use it to generate data for our machine learning algorithms. So our main research goals is first to find the optimal machine learning method to model a 30 and 300 bus system, and we measure this by computational cost, model accuracy, and adherence to physical laws. And then we also want to assess the viability of machine learning to model larger scale power grids. And we want to investigate optimizing metrics and find a model that would allow analysis of extreme conditions or deviation to the norm, like a lightning strike takes out a power line. Is the same machine learning model then useful, and what is the variation compared to before that power line was taken out?
So in order to be able to use these machine learning algorithms, we had to come up with a fairly extensive data set, and we used MatPower in the MATLAB system in order to be able to create those. MatPower either converges or doesn't converge depending on what type of data that you gave it. So we started with a basic traditional 30 bus system and a traditional 300 bus system based on the US power grid. The 30 bus system was, the data was taken from 1961, and then we perturbed all of the values for the input of power, or two of the values for the input of power, and within a 10% range around the original values. We tried about 30,000 of these simulations, and only just over 20,000 of them were successful. And so we split that using an 80-20% training and testing data set. For the 300 bus system, we were able to generate about 25,000 simulations, and again, only around 20,000 of them were successful. And again, we split them into an 80-20 split. So we used a neural network algorithm that is referred to as a multi-layer perceptron algorithm, which involves hidden layers as well as an input layer and output layer on either side. For the input layer, we have PD and QD, which is the real and reactive power coming from each of the buses. And then the output was the PG, which is the generator power, what you want to set the generator to, and the voltage. So that's per generator. So the input for our system would have for the 30 bus system, we would have 2 inputs for all 30 buses. So we had 60 inputs, and the outputs of the system was 12 because there were only 6 generators involved with this 30 bus system. In between the inputs and the outputs, it goes through hidden layers. And as you take each data point and run it through the system, the weights and the biases of each one of these layers are adjusted accordingly using back propagation. In between each hidden layer, we also employed an activation function to tone the data for each layer, and then we did a batch normalization to kind of refine all of the data from one layer to the next, so we would reduce the noise. So we tried, for the 30 bus system, we tried multiple different variances of the hidden layers, the nodes, and the activation functions. We wanted to see if we could find some sort of optimal system. But the 3 metrics that we were using was the validation accuracy, which is an accuracy metric, the legality rate, which is how well each of the outputs adhere to the constraints we were speaking of before, and then the average cost deviation, which is how well the predicted cost deviated from the actual cost. But each of these came up with a different set for its optimization level. We have in the blue here, we have is the highest legality rate, the red is the lowest cost deviation, and the green is the highest accuracy. Just going with the highest accuracy wasn't necessarily what we wanted to do. We obviously wanted very high accuracy, but we ended up going with the red one because it not only had a relatively high accuracy at 99%, it also had a significantly lower cost deviation and a higher legality rate than this bottom one. The other thing we found with the 5-layer system is that there was a lot of fluctuations as we went through the epochs, and with each time we ran the system, and the one that we chose did not have that kind of fluctuation, so it's a little bit more stable. So we went with 3 hidden layers with 100 nodes per layer and the rectified linear unit activation function. So I mentioned the term epoch, and epoch is one training pass. So as we take the data and we put all of the data through through all the hidden layers. That is one epoch, and we ended up making decisions to do 500 epochs, and this is how the model accuracy evolved through all the different epoch layers. So, in terms of the accuracy, you have the blue line is the training set, and then the orange line is the testing set. There's a lot more noise with the testing set, which is to be expected because it's not being trained on that. But the noise is relatively small. If you look at the y-axis here, we're really only varying towards the end of it a few percentages. So it's the accuracy is relatively high for this particular model. The model loss represents how different or how good of a fit the model was to the training data. And in this case, we have basically nothing in terms of model loss. And the training and testing data lines are right on top of each other, which indicates a high level of accuracy. We also tried a second type of model called an XGBoost model. This is similar to a random forest, but not quite. It is a decision tree-based regression model. It's relatively new in the world of machine learning, and we wanted to test it and see how well it did, and whether or not it would be useful for our purposes. So similar to that, we tested a whole bunch of different variations. In this case, we kept the depth of each tree at 3, and we wanted to test out the number of trees and see how well we could do. One of the things that we noticed about this, we still had 3 metrics. The average cost deviation and the legality are the same, but the R-squared score is a little bit different from an accuracy measure. It's really more of a goodness of fit measure. And we can see as the number of trees increases, the R-squared score increases, but the legality rate decreases. That's the major difference between this one and the other one. The good thing about it is that the legality rate really only varies a few percentage points in 1,000 trees. So that's, even though we're losing a little bit of legality, we're not losing enough to really have to worry about. Unfortunately, it requires a significant amount of computational power to run these, so we were not able to do it for smaller increments. In order to really be able to optimize the system, we would want to do it for smaller increments. There's a point at which, for these models, the R-squared score goes up, and then it'll peak, and then it starts to come back down, which represents an overfit. So what we would want to do is do significantly smaller increments, and then see where that peak of the R-squared score would be. But again, unfortunately, a laptop doesn't quite have the power to do that. So for our purposes, we did use the last one on here with the highest number of trees, even though the legality rate at the top was the highest for the blue one. We tried it on the 300 bus system, and unfortunately, we're extremely unsuccessful. We had it clearly stagnates. Your left-hand side graph is the 30 bus system graph that I showed you earlier, and then the right-hand side is what we were getting for the 300 bus. It indicates that there's just no training or no learning going on in the system. We tried lots of different data sets. We tried lots of different types of data. We fluctuated the data more. We did all sorts of different things. And I think really what it comes down to is that we just didn't have enough data. And similar to running the XGBoost systems, it requires a lot to run all the data through the map power system. And just making those 20,000 for the 300 bus system took a number of hours. So trying to make, say, 800,000 would have been the entire workshop. So we couldn't quite do that. But that would be something for future work for sure. So we did find that our machine learning algorithms were significantly faster than the map power system by orders of magnitude, multiple orders of magnitude. So that's a good thing. That is helping us get on our way to having a faster system. We did find that the neural networks, because of the structure of the multilayer perceptron, varied in terms of what the metrics were and what we really wanted to push for. So it's possible that at another system we may want to really focus on legality rate, in which case we would choose different configurations for the neural network, and then be able to run it through the system, depending on how many buses we have and what the situation is. The XGBoost system was able to achieve high accuracy and legality. The XGBoost legality was actually higher for the most part than most of the configurations of the neural network, even though we were losing legality as we went up in trees. So ultimately, the legality rate for the XGBoost system was higher than the rest of them. And unfortunately, we were not able to expand either one of them for a higher level system. But that would be something that we would like to do in the future. We have quite a few things that we wanted to do with this project, but we're slowed by mostly computational time and just kind of trying to figure these things out. I mean, if each one of these runs takes a long time and then we're changing configurations and running it again, we spend a couple days just trying to figure out which ones we wanted to use. So one of the things we want to do, as I just said, is we want to generalize it for the higher nodal systems. A 30-bus system is a relatively small system, so the hope would be that we'd be able to generalize it for, say, the entirety of North America system, which I don't know how many buses that is, but it's significantly more than 30. We also want to look at optimizing the XGBoost model for higher estimators, which are also the decision trees. We also wanted to look at optimality classifications. So that means that when we get appropriately predicted outcomes, a certain subset of those would be what we would want to define as optimal. And we don't know exactly how we would define that optimality, but we would want to investigate exactly what optimal means in terms of these grid systems per bus number, and then be able to classify both of these outputs by it's either optimal or it's not. And then, of course, the lightning strike, we would like to be able to make sure that our machine learning algorithms can actually deal with a lightning strike and deviations from their normal operating behavior. We would like to thank Chris Oman and Mark Rice from the Pacific Northwest National Lab. We had a lovely Skype talk with the two of them, along with a couple of their colleagues, and the IEU from North Carolina State, who sat in with us and did a lot of computational things and added another laptop to the system, which was always a plus. And of course, Adam Materian and the rest of the group here. And
Great, thank you. Questions?
I have a question.
yes.
So, when you're looking at the legality rate, I was thinking that, like maybe for example, 1 volt gets lost in the solution, whereas like 100 or 1,000 volts get lost in the solution. That would be a greater problem. So I was wondering if there was a way to measure like how badly are the physical laws being violated when you calculate this coefficient, or if you look at this at all. I don't know if that makes sense.
That's not necessarily something we looked at so much, because in this scenario, even if you're off by 0.1 of a volt, but you're outside those constraints, then it's still going to be a failed system. They aren't soft constraints where you roughly need to be inside them. They're very hard. If you get at all above this limit, you're either going to cause a lot of damage to the system, and in the case with a lot of the generator constraints, you're going to break your power plant if you ask too much of it, or you're going to get power outages if you have any issues with buses.
I see, thanks.
There's another question over.
Oh, yeah.
Okay.
Were you able to compare the cost? You said your ultimate goal was to reduce the cost. Your optimized equation was a cost equation, correct?
Yeah.
Was there any cost comparison there?
We did an average cost deviation comparison, which is similar to what you're talking about. We did not specifically take one particular instance and then compare the cost from this model to this model. We didn't get into such specifics like that, more on a global scale.
But generally, the machine learning was able to accurately anticipate the cost of the system.
Yeah, the cost deviations were on the order of thousands, so not too bad.
There's another question? Yeah, go ahead.
Yeah, I'm just wondering, did you also compare your results from the machine learning to the traditional numerical results in terms of accuracy?
Yeah, so that's a lot of what both these R-squared values are. That's a goodness of fit between the machine learning output versus what numerical methods outputs were for the exact same simulation, and then same with the validation accuracy. So the validation accuracy we were able to get within like a 1% deviation for that red mark, and then on the R squared score, able to get it within like what, 0.12.
So I have a related question on the other table.
Yeah.
So you're running the machine learning, it gives you the validation accuracy, and then you're observing the legality rate. Is that correct?
Yes.
Yes.
Okay. So is there any hope of, because the machine learning is ultimately using an optimization, minimization algorithm, is there any hope of having some sort of simpler constraint for the legality rate that you could add to that cost function? So that when it does the optimization, it will run multiplier or penalty parameter, so that when it does the optimization, it might actually try and boost the legality rate.
Yeah.
So legal rate basically checks all the constraints on the obvious problem. So we had implemented it separately in the Python code.
But is there some simple statistic or something that you could sort of translate that into and do that legality rate, maximize that in an automated fashion?
For some of them, likely, because a lot of them are very easy constraints to check. Like if you have a generator value, you can see if the generator is inside or outside the min or max of them.
Sure.
Others are dependent upon the entire network. For instance, like the energy moving into a bus has to be the same as the energy moving out. So you have to check all the buses that it's connected to, which you could do feasibly in a fully connected neural network, but would be more difficult. It's not something we
And
investigate.
it's a question of whether the machine learning package allows you to have that, or you have to do a custom thing, right?
I'm sure.
So you can
Yeah.
All right.
Did you use the same neural network on the 300 node?
No.
Or did you try? Okay.
So for the neural network, so as you mentioned, the first case, the topology changes your algorithm. So the 30 case will not work in a 300 case, and we changed it. We tried it even with since nothing was working. I tried it with the same neural network model that was for the 30 case. It still didn't work. It's just because it's come down to us because we need to generate like huge tons of data. We did it for like 25,000, and it took like hardly maybe for a day to just generate 25,000 data, and the author did it for 800,000, I think. So which is a lot.
What's the most nodes that you went up to?
So we checked up to background I checked up to 500 nodes and changed variations, but that was the ultimate. Like for me, yeah, that worked best for 100 and 100. And just to answer your question a bit more, I think you were talking about the cost. We actually plotted it was the true cost and the predicted cost, which are exactly overlapping. So that was one of the good things in the model. So with the 3 layers, 100 and 100, with the activation with ReLU, we had exactly the true cost and the predicted cost. The graphs were matching. So that was a good thing. Yes, go ahead.
From experiments, I'm wondering if you have any idea what kind of topology is best for your algorithm.
We really only checked 2, and it'd be unsure how helpful that would be because the topology is given by the like the power grid system. So if we say your topology is wrong, power operator can go, oh, we're just going to change the whole grid system. Yeah, that'd be like a major issue with that classification. It could help with some grids, and these would work. Some grids with these grids it wouldn't work. But grid operators can't just change the whole system if a machine learning method doesn't work for it. Yeah, we don't analyze a lot easier.
Okay, comments?
Yeah.
When the last couple of weeks and months back at P&L, when we were formulating this project, we really didn't know where it was going to go or what kind of answers we would get because it really hasn't been investigated at all. So I'm really excited to see that we have some baseline results and we have a direction that we can take this when I go back to the lab. It's very impressive already. So I'm you guys did great work, and I'm really happy with kind of what you were able to produce. And I know that we had a lot of initialization problems, getting started, but it was good. I really,
We got to experience a power outage as well.
Yeah.
People in the control room were trying to shut your investigation. Oh, yes, thank you, guys.